When they asked me to do this talk, they told me kind of what she just touched on. The point is, you guys have been sitting around all day doing problems on a piece of paper. The point, the goal here is, how does calculus and math leave the classroom? And it's certainly a big factor in my research. That's touching on medical imaging and mathematics. So what we're going to do today is we're going to first start talking about noise in general, what it means to be a noisy signal, how we get rid of noise. Then we're going to motivate medical imaging and research, and we're going to talk about how it works and the math behind it. So first off, if you watched the World Cup at all last summer, the one thing you couldn't escape was the buzz of the vuvuzela. But what that really is sound is just a one-dimensional wave coming in, and you can consider that buzz of the vuvuzela to be, some noisy corruption. Or, some people may have loved it, but so you may remember this sound. On a gloriously sunny day here. I don't know if you guys can hear that too well. So you can't escape that buzz, but as it turns out, with some pretty simple signal processing techniques, you can escape it. And I think they figured out how to do this about halfway through the World Cup, and some TV programs offered you the opportunity to turn it out. So if a sound signal is a one-dimensional signal with some noise, really an image is a two-dimensional signal. And if you've ever seen any spy movie, there's always the same scene in each one. You get the nerdiest character, he sits up at a computer, and the hero looks over his shoulder, and they're looking at some blurry screen on the monitor, and they're looking for a clue or something. And the hero then points out and he says, what's that? Can you enhance that? And the nerdy guy smacks a few keys and says enhance. And then the next thing you know, this noisy, blurry picture turns crystal clear. The hero finds his clue. Everybody goes home happy. And that's just two-dimensional denoising. So in this case, one of these corrupted pictures is actually of Lady Gaga, and the test here is, can you tell which one? By a show of hands, who thinks it's A? Who thinks it's B? Who thinks it's C? Wow, I did pretty good with this one then. If my clicker will work, we can have the big reveal. B. That is a Christmas tree, not a pop singer, and that's Oscar the Grouch. So what's really going on here is all we have access to is this noisy image. And we're not going to be able to reconstruct it exactly, but, as math gets more and more advanced, we get better and better reconstructions. The point is, noise is everywhere. If you think of your TV, that's denoising a signal. Your radio, that's denoising a signal. You're on a cell phone, that signal is traveling all the way up to satellites. It's going to encounter some noise, and the goal is you want to take the noisy image and get out the true signal. And so what I work on is with medical imaging, and where is it more important to get a crisp image than when you're screening for potential problems. Everybody's body is different, so when you're sending something through, trying to image it, there's going to be some noise. So we're going to further motivate research in medical imaging. The first point is there's a lot of money involved in medicine. Take, for example, Dr. James Andrews. If you follow sports at all, and one of your favorite players gets hurt, 9 times out of 10, they go to Dr. James Andrews, because he's the best. That other one time, usually they don't like what they hear, and then they go to him for a second opinion. You can see this list of, a who's who of athletes, and things are working out pretty well for Dr. James Andrews. He owns a jet, a baseball team, and his practice brings in $60 million in revenue. So, for one, it can make you rich. But on a far more somber note, it seems like everybody knows somebody whose life's been affected by cancer. As you can see here, 23% of all deaths in the United States are from cancer. If you look at the raw numbers, each year, 766,000 men, 713,000 women are diagnosed with cancer, and then of those diagnoses, 292,000 men and 269,000 women die. And that rate's not good enough. So what can we do to improve it? Well, the earlier you detect it, the better chance you have of surviving. If you look at this chart, we have 4 types: prostate, ovary, lung, and pancreas. And the point of the chart is when each line reaches its full width, that's when 100% of the cases have been diagnosed. So if you look at prostate, almost all the cases are diagnosed in stage 1, and you have a very high survival rate. That's good. But if you look at lung, you don't see most of the diagnosis until stage 4, when you're already at a 20% 5-year survival rate. So what we have to do is we have to image these things better so that we can detect earlier, but without a high false positive rate. So what does that mean? Well, if you go to the doctor and you have a screening for cancer, comes back positive, but in actuality you didn't have cancer, then that leads you down a road of unnecessary, potentially invasive biopsies, and also studies have shown psychological side effects of being told you have cancer when you don't. And it's to the point where the American Cancer Society only recommends mammograms for women over 40, not always, but in general, because the false positive risk is outweighing the potential benefits of getting people screened earlier and earlier. And that's not a good reason. We need to improve our techniques. So how does it work? Well, medical imaging pretty much starts with the X-ray. In 1895, you shoot X-rays through the body, put some film on the other side, and you get a nice picture. But then as computers came around, we got computerized tomography or CT scans. And how do they work? Well, instead of one X-ray going through, they take X-rays all around the body. And then so they have all these different measurements, and they combine them together and do some processing to get just one picture from all those different X-rays all the way around the body. So you see, the more X-rays you take, the more angles you're using in your X-ray, the sharper the picture you get. This one was a simulation with 120 angles. It's sharper and crisper than the one with 30. But what happens when you get an X-ray, you're exposing your patient to possibly harmful radiation. You've been to the dentist, you get your teeth X-ray, and they give you that big lead vest. The reason they give you that is to protect your insides from radiation. So if they're giving that to protect you when they're imaging your teeth, can you imagine 120 X-rays going through your body just to make one picture? So what else? If CT and X-rays can be dangerous, what else can we do? Well, we have PET scans, which are nuclear-based. We have MRIs, ultrasounds, which use sound waves, electrical impedance tomography, which uses electrical currents, and then we have what we work on here, which is optical tomography. If we don't want to use radiation because it's possibly harmful, what's better than, good old-fashioned laser light? So that all sounds great, but what's the catch? Well, the math is a lot more complicated behind imaging your body with laser lights than it is with X-rays. So first, how an X-ray works: you got a source, and you got a detector, and the X-ray goes straight through source to detector, and you have this nice relationship called the radon transform, in which the log of the source intensity over the detector intensity equals the integral along this line of the density. This density is going to tell us where there might be a tumor, because if we have a general idea of what the density of your body should be, and we hit a spot that doesn't make sense, then there's a good chance there's a tumor there. And so this would be your density function matching up with this cartoon tumor. So it works out nicely because the source goes straight through, that we have this technique called back projection, which reconstructs our density function from that radon transform information. And then if you do the CT, remember that's doing X-rays at all different angles. We have this simulation here. This would be somebody's brain, I suppose, with a Clemson Paul. You would do a CT scan, X-rays all around, and then this pretty picture here encapsulates all the data of radon transforms for 180 different angles. You back project it, you get your reconstruction. Looks pretty good, but once again, that was with 180 X-rays. And our point was we're trying to avoid doing all those X-rays. And so back to the optical tomography. So what makes this harder? Why am I researching this? Well, in the X-ray case, the X-ray goes straight through and you just read out what happens on the other side. But when you're sending in photons of light, they bounce around, they get absorbed, they scatter. If you think about this laser here, you know, if I shoot it through, it doesn't go through and out the other side. It just kind of makes my skin glow because the photons are diffusing around and spreading around. A little more math for you. It'll be governed by a second derivative type thing. Second derivative captures the diffusion versus the first derivative, which would have been rate of change. So since the photons are scattering all around, instead of putting the detector right on the other side, we send in a source and we have to detect all around. So we can't do that back projection trick like with X-rays. We have to do what's called an iterative reconstruction. Taking a step back to talk about the general framework, sort of the field that they consider my research in is called inverse problems. The forward problem would be defined as, you know X, you know F, find Y. That simply is evaluate the function. Whereas the inverse problem would be, you know Y, and you know F, how do you find what X is? Well, it works pretty well when you have something like sine. You just evaluate inverse sine and it'll give you X. Or it works well in the X-ray case, we're able to just back project. But, you know, in this optical tomography case, because everything's bouncing around and we have to detect all around, the function's not so simple. The function's more like sending a laser source into your head and detecting photon densities all around your scalp. How are you going to invert that? That's not so simple. Now, so what we end up doing is we reformulate it as a minimization problem, and as you guys hopefully will remember, in an optimization problem, you know, you need a derivative, you find the critical values, all that good stuff. Well, what's the derivative of sending lasers into your head and seeing what comes out on the other side? So that's the point, is we're working on a very complicated problem with a tough model to work with, and so we're developing algorithms that can help us solve it, and, you know, hopefully one day compete with the accuracy of these other imaging techniques with, you know, harmless light. So what do? We simulate the experiment. We've got sources and detectors all around, and we're going to send in a bunch of different sources one by one, and then at each source we have to detect what, remember, because the photons are spreading around. And so we do this for a bunch of sources. We're now armed ourselves with lots of data, and with this data, we can start to reconstruct our image. This is an earlier version of the algorithm we're currently working on, and as you can see, slowly, step by step, slowly, we start to isolate tumor 1 and tumor 2 from that simulation. Go on. And so that's pretty much what I'm working on, is, you know, taking this ill-posed tough problem and getting it to the point where we can actually simulate some real data and start detecting tumors with laser light. To hammer the point home about math not being just your homework, but it being, you know, something you're going to need, and don't give up, regardless of how things went today. Forbes released its 10 best jobs in America in 2011 back in January. Mathematician was number 2. So, yeah. Woo! There you go. All right, and I just wanted to close with that, and then some quick thanks. I would be remiss if I didn't mention that my research is supported by the National Science Foundation, just like this competition. And also thank the organizers for letting me / volunteering me to do this. And thank you, the audience.